Hi everyone, in this section, we prove that the set of rational numbers is a countable set. First, let us recall that the set of rational numbers, typically denoted by Q, consists of elements of the form P over Q, where P is an integer, Q is a non-zero natural number, and we often require that P and Q are co-prime to each other, meaning that they do not share any common factor other than 1. This requirement is to exclude the multiple representation of the same rational number. For instance, 1 over 2 and 2 over 4 both stand for the same number. Yet, with this requirement of coprimality, we will use 1 over 2 to represent that number rather than 2 over 4, because 2 and 4 are not co-prime to each other. They share the common factor, which is equal to 2. Our intuition might suggest that the number of rational numbers is much more abundant than that of the naturals. For instance, between 0 and 1 there is no other natural numbers, yet you can put infinitely many rational numbers inside this interval. Indeed, the distribution of rational numbers on the real axis is dense, meaning that no matter which spot we're on the real axis, we will always be able to find some rational number as close to the spot as we want. Thus, it might be slightly surprising when we claim that the rational numbers form a countable set. However, we will see it follows naturally from the propositions of countable sets we have demonstrated in the previous section. We will provide two approaches to prove this statement. In our first method, for each natural number n, we construct a set Hn, which is a subset of the rational numbers consisting of irreducible fraction p over q, satisfying in addition that the absolute value of p plus q is equal to n. For instance, H0 is clearly the empty set. H1 consists of only the rational number 0. H2 consists of 1 and negative 1. And H3 consists of positive negative 2 as well as positive negative 1/2. We see that given an arbitrary element p over q in Hn, neither the magnitude of p nor that of q can be too huge. In particular, for each n, Hn is a finite set. Now clearly, q can be written as the union of all those Hn where n varies among all natural numbers. In other words, q is a countable union of countable sets. Thus, q itself is countable. Alternatively, or perhaps even easier, we can proceed by considering a function whose domain is q, whose codomain is the product set of z cross n, where each rational number p over q in its irreducible form is sent to the ordered pair p, q in the product set. If two rational numbers are sent to the same ordered pair, then they will share the same numerator and the same denominator, which means they must be the same rational number. Hence, this function is injective, indicating that the cardinality of q is less than or equal to the cardinality of z cross n. Since z is countable, n is countable. As the product of two countable sets, z cross n is also countable, which in turn implies that q is countable as well.